Welcome to Lecture 47, whose twin subjects are space and time and how relativity affects our ideas of space and time. Now, in the previous lecture, I gave you just one simple idea, principle of relativity, the idea that the laws of physics, all the laws of physics, mechanics, electricity and magnetism, everything is independent of your point of view. That is, doesn't depend on your frame of reference, that the laws of physics are the same for all observers as long as they're in uniform motion. That was one simple idea from that lecture. This lecture is going to seem a lot busier. There's going to be some fairly heavy math. There's going to be some diagrams that are going to be a little bit confusing at first, and I'll try to explain them very carefully and thoroughly. But it's not really going to be busy because all it's going to be is an examination of the implications for the nature of space and time of that essential principle of relativity, and I'll be very careful to show you exactly where we're applying that principle. We are going to get quantitative. We're going to get more quantitative than I do, certainly, in my book, Simply Einstein, which is a book about relativity for non-scientists. We're going to get more mathematical than happens in several of the other great courses that deal with relativity subjects. We're going to get a little bit more mathematical because we want to understand quantitatively how these things come about. We want to understand in this lecture quantitatively how it is, not just that it is, but how it is that our notions of space and time, our common sense notions, notions that have been with humankind for millennia, simply aren't right. They aren't completely wrong. We don't have to throw them away completely, but they aren't right either, and we have to modify them. And before we do that, I have to begin by defining one of the key concepts in relativity, a concept that you're quite familiar with, and that's the concept of an event. What's an event? An event is an occurrence that you specify by giving both its place and its time. So you tell me that such a place and such a time something happened. A good example of an event is your birth. Your birth occurred at a particular place, your birthplace. It occurred at a particular time, your birth date. But your birthplace is not an event, it's a place. Different things happen at your birthplace. You've long since been born, but things are happening right now, other events at your birthplace. Your birthplace is not an event. Your birth date is not an event because on your birth date in your birthplace, events were occurring at other places besides your birthplace. So place and time are not events. An event requires both place and time. It's an occurrence specified by giving its place and its time. That's something we all know. Mathematically, an event is specified by giving four numbers. It's three spatial coordinates on an arbitrarily chosen x, y, and z coordinate system, and its time coordinate, that is when it occurs, relative to some arbitrary zero of time. As always, coordinate systems are mathematical artifacts that we human beings impose on reality. But if we want to describe an event, then we have to impose four numbers on reality. We have to tell where, that's three numbers, and when, that's one number. Why it is one time and three space, that's kind of a profound philosophical question, but that's the way our universe seems to be. Three spatial dimensions, one time dimension. All observers agree about the reality of events. Everyone agrees that you were born. What they may disagree about are the space and time coordinates of your birth or any other event, and about the time interval and spatial distance between two events. And in this lecture, we're going to be focusing on those latter two things, the time interval and the spatial distance between two events. And I want to show you quite rigorously that they cannot be the same for all observers. And there's no contradiction of that with the principle of relativity. The principle of relativity does not say all observers will measure the same values for all things. What it does say is that all observers will come up with the same general laws of physics and how those laws operate. And those laws will include Newtonian mechanics, as appropriately modified to be relativistically correct, and Maxwell's equations of electromagnetism, which do not need any modification because they're relativistically correct. And because, as we saw in the previous lecture, the laws of physics, including Maxwell's equations and their implication that light goes at speed c in vacuum, because that's got to be the same for all observers, notions of space and time, measures of spatial distances, and temporal intervals cannot be the same for all observers. And that's what we want to plunge into here and have a look at. So I'm going to begin with a math alert. Heavy math is coming here, and it's going to give us, as heavy math has in the past, valuable insights about physical reality. Now again, the heavy math isn't that heavy. It's high school algebra, but it gets just a little bit messy. But if you really want to understand how we go from the principle of relativity, that the laws of physics are the same for all observers in uniform motion, to actual statements about what different clocks will read about the time intervals between different events, then you've got to do this math. When I'm doing relativity for complete non-scientists who don't want to do any math at all, I just state the results I'm going to derive here. But you'll come to understand those results and how they follow rigorously from the principle of relativity. So let's go into our math alert. Here's our big screen where we do our math. And I would like you to imagine a device which I'm going to call a light clock here in quotes. And the light clock is just a timekeeping mechanism. Like any other timekeeping mechanism, it has some periodic happening. The swinging of a pendulum, the vibration of a quartz crystal, whatever it is that sets the timekeeping of a clock. In this clock, the timekeeping is set by a light source which flashes, sends a light beam up to a mirror, and goes back down again to that light source. So this is our clock, and the ticking of that clock consists of the interval between the light leaving the source and the light returning, bouncing off the mirror, and returning to the source. And you'll notice that this light clock has a length L in its long dimension. Now, I want to emphasize right off the bat, and I'll say this again several times, even though this device is a rather specialized construct, and it involves the properties of light, obviously, nevertheless, the conclusions we draw about this light clock are going to be conclusions not about this specific device, but conclusions about any clock, including a regular, ordinary clock with a sports watch or whatever you've got, because they are ultimately conclusions about time itself, not about clocks, but about time. So let's look further at this light clock. I'm going to define two events. Event A is the light flash leaving the source, heading up toward the mirror, hits the mirror, bounces off, comes back, and when it returns to the source, that defines event B. And I want to ask the question, what's the time interval between event A and event B? How long does that take? Given that I know the length of the light clock is L, and I know something else, I know that the speed of light is c, assuming there's a vacuum in here, so we have light traveling at speed c. So let's plunge into the math and see if we can figure out the answer to this actually relatively simple question. And let me be very careful when I ask any question in relativity. What's the mass of that object? How much energy does that object have? What's the time interval between this and that? How old is this person? All those questions are questions that I really have to say, what's the reference frame? Actually, the first question about mass wasn't such a question, but the others were. I have to generally ask or answer the question, what reference frame am I talking about? Because many quantities in physics that we think of as being absolutes, in fact, depend on your point of view, on your frame of reference. So I'm going to be very careful here to specify I'm asking this question, at least at this point, in a reference frame which I will call S prime, and that's the reference frame in which this light clock is at rest. Is the light clock moving or is it at rest? Those are meaningless questions in relativity. There is some reference frame in which you are at rest with respect to the light clock, or the light clock is at rest with respect to you, or the light clock is at rest in that frame of reference, however you want to put it. That's the frame of reference which I'm calling S prime. And in that frame of reference, by definition, the light clock is at rest. And in that frame of reference, the light travels a round-trip distance 2L, up and back. It travels at the speed of light, which is c. Distance is speed times time. So time is distance over speed, 2L divided by c. And that's the answer to our question. What's the time between A and B, events A and B? It's 2L over c, and I'm going to call that delta t prime, prime again standing for this reference frame S prime, in which the light clock is at rest. So that wasn't very heavy math. Same situation. Let's ask the same question. But now let's ask it in a reference frame S, in which the light clock moves to the right at speed v. There is such a frame. If I had been in the original frame S prime, all I had to do was move to the left with speed v in that relative to that frame, and to me, the light clock would be moving to the right with speed v. So I'm now considering myself to be in a frame in which the light clock is moving to the right at speed v, and in that frame I'm asking the question, what's the time between those two events A and B? Now, if we didn't believe relativity, we would in fact come up with the same answer we did before. And the reason we would is because we would have the light, you'll see, traveling a longer path. It's traveling those diagonal paths. But it would have been going a little bit faster because it would have had the motion of the light clock vectorially added to the motion of the light. I say vectorially because they're not in the same direction, but they're not in exactly opposite directions either. And we would have come up with the same answer. We're not going to come up with the same answer here, and that's going to be our first insight into the difference between time in classical physics and time in relativity. The total distance now is twice this diagonal path. That much plus that much. Twice either of those diagonals. The light clock is moving at speed v in this reference frame that we're talking about. So whatever that time interval is, and I'm going to call it delta t without the prime because we're not in the prime frame now, we're in the frame S, which doesn't have a prime. The distance the light clock goes in that time delta t is going to be v delta t. Distance is speed times time. We want to figure out twice that diagonal. Well, here's how we can figure out the diagonal. The tall side here is L, the length L. The short side is half the distance the light clock goes, or v delta t, divided by 2. And we've got a right triangle, and we know the Pythagorean theorem that says the hypotenuse squared is the sum of the squares of the other two sides. So there it is. The hypotenuse is the sum of the squares of L and v delta t divided by 2. Put that all in, square it, take the square root. That gives me one of those diagonals. There's two of them. Double it. How fast does the light go? Here's where we're sneaking in the principle of relativity. Light goes at speed c, period, as far as any inertial observer, anybody in a uniformly moving reference frame, anybody in a frame of reference that obeys the law of inertia, an unaccelerated reference frame, those are all ways of describing the same thing, moves at speed c. I am not assuming that the light gets added to at the speed of the box. Remember the examples we did in the previous lecture about relativistic velocity addition. And if you did the challenge, you found that you can't add to the speed of light. The speed of light is c in all reference frames, and I'm going to assume that here, and I'm going to state that light speed is c. Distance is speed times time, and consequently time is distance over speed. There's the distance we traveled in this reference frame. There is that distance divided by c, and there's the answer, delta t. Whoops, not quite, because delta t is hiding also in here. That's why we had to have a math alert. We've got to somehow get the delta t out of there. So here was our result. Delta t is twice that one diagonal, two diagonals worth, and we got to get the delta t out of there. So we've got to do some algebra. So we'll multiply first by the c, get rid of it in the denominator, it goes over there. Now we will square both sides, c squared delta t squared. On the left, we take the square root off. On the right, and we square the 2 that was outside the square root, and that becomes a 4. Continuing with the algebra, c squared delta t squared on the left, 4L squared, and now I've just squared out this second term. That's v squared delta t squared over 2 squared, so v squared delta t squared over 4. Next, I'm going to distribute the 4 through the two terms. C squared delta t squared is now 4L squared, and that 4 wipes out the 4 in the denominator, and we've got simply v squared delta t squared on the right. This is the heaviest math. We're almost done. There's what we have now. Now we have delta t still in two places, but we can begin to get it together because I can move that term over to the other side of the equation. I have c squared delta t squared minus, subtracted this term from both sides, v squared delta t squared is now what's left on the right, the 4L squared. Now I can factor out that delta t squared because it's common to both terms. C squared minus v squared times delta t squared is 4L squared. Factor out the c squared, that gives me a 1 here. It gives me a v squared over c squared here, and it divides the right-hand side by c squared, and it gives me that. Take the square root. The 4L squared over c squared becomes 2L over c. I've flipped the equality left to right, which is also fine. I've taken the square root of that term, and I've taken the square root of delta t squared to get delta t, or write it like that. And now, look at our original case in frame S prime. Delta t prime, we found, was 2L over c. Well, there's 2L over c sitting there in this expression we derived that has delta t rather than delta t prime in it. Those expressions are the same. And so delta t prime becomes square root of 1 minus v squared over c squared delta t. or delta t prime, is delta t times this correction factor, which if the velocity were 0, that would be 0, and this would be the square root of 1, which is 1, and the 2 times would be the same. But if the v is not 0, if there is relative motion between the two frames, then they will measure different values for that delta t, for that time interval between those two events. That phenomenon is called time dilation. And time dilation is one of the simplest and most perplexing, nevertheless, ideas to come out of applying relativity. Let's look at time dilation a little more. Let's do an anatomy of this important equation. Here's delta t prime. It's delta t times this square root factor. What do we have on the left? On the left, we have the time between two events as measured in a frame of reference where they occur at the same place. Let me make it clear what I mean by that. In the reference frame of the light clock, the light left the bottom of the clock and it came back, and that was occurring at the same place because the light clock wasn't moving in that frame. There's delta t. That's the time between the two events in a reference frame where they occur at different places. And they occur at different places because in this case the light clock is moving with speed v, the relative speed of the two frames. That's the anatomy of that equation. People often describe time dilation by saying incorrectly that moving clocks run slow. Moving clocks don't run slow. Well, there's a way to understand that statement if you use it carefully, but what's more correct is that the time between two events is shortest in a reference frame where the two events occur at the same place. Let me give you a famous example. Here's a trip between Earth and a star in a spaceship that can go at 0.8 the speed of light. So on the left, I've got the Earth and the spaceship just starting out from Earth. The Earth and the star are 10 light years apart. The clocks on Earth and star read 0 at the start of this trip, and the clock in the spaceship also reads 0. The spaceship zooms along at 0.8 of the speed of light, and we want to know what's going on when we get there. Well, how long does it take? The ship has gone 10 light years at 0.8 light years per year. That comes out 12.5 years in the Earth-star frame S. What happens in the ship frame? Well, in the ship frame, we apply this idea we just developed of time dilation. Delta t prime is delta t modified by that square root of 1 minus, in this case, 0.8 squared. 0.8 is 0.64. 1 minus 0.64 is 0.36. The square root of 0.36 is 0.6. 0.6 times 12.5 is 7.5 years. So at the end of this trip, the Earth and star clocks read 12.5 years, and the ship clock reads 7.5 years. That's a picture in the frame of reference of the Earth and star, not necessarily the frame of reference of the ship. Let's ask a question about distances. In the Earth and star frame, that was a trip of 10 light years. In the ship frame, that was a trip that took 7.5 years at 0.8 the speed of light. Well, how far do you go at 0.8 the speed of light if you travel for 7.5 years? You go 0.8 the speed of light times 0.75 years, and you get 6 light years. So as far as the ship is concerned, the Earth and the star are not 10 light years apart, but 6 light years apart. That's called length contraction. That's the idea I introduced that Lorentz and Fitzgerald had thought would solve the Michelson-Morley problem. It sort of does. But it's not that the ether is squishing things, it's that measures of space and time are different in different reference frames. So anatomizing this length contraction equation, L prime is the length of an object or the distance between two objects in a frame of reference where they're moving with some speed v. L is the length of the object or the distance between two objects in a reference frame where they're at rest. And v, again, is the relative speed of those reference frames. Let's draw a few more conclusions about this before we wrap up. One of the biggest ideas about time and relativity is that simultaneity, the idea that two events occur at the same time, is relative. If measures of time are different in different reference frames, so is this measure of simultaneity. And here's a picture in which two identical airplanes pass each other. And in a frame where they're both moving at the same speed, their noses and tails coincide at the same time. Let me define two events. Event A, I'm going to call the tail of the upper plane coinciding with the nose of the lower plane. Event A is happening on the left side of this diagram. Event B is the nose of the upper plane corresponding or coinciding with the tail of the lower plane. That's occurring at the same instant that I've pictured here and it's occurring on the right side of the diagram. Those two events are simultaneous. But they're only simultaneous in this particular frame of reference where the two airplanes pass each other going at the same speed relative to that frame of reference, but in opposite directions. Let's now look in a different frame of reference. Let's look at the frame of reference in which the upper airplane is at rest. Now you'll notice I've drawn it longer than I did before because now I'm in its rest frame where it has the greatest length. And I've drawn the other airplane even shorter than before because it's moving faster relative to the upper airplane than it was relative to that frame for which they were both moving in the same direction. And now look what's happening. The nose of the upper plane is corresponding to the tail of the lower plane. That is event B. So event B is occurring now, but event A hasn't occurred yet. Now event A occurs when the lower plane gets so its nose coincides with the tail of the upper plane. So in that reference frame, B occurred before A. Now let's look at a different reference frame in which the lower plane is at rest. It's the opposite. The lower plane is now longer because we're in its rest frame. The upper plane is shorter. Event A occurs before event B. Events that are simultaneous in one frame of reference are not simultaneous in another. That idea gets you out of most of the contradictions you think you discover in relativity. Events that are not simultaneous in one reference frame are not simultaneous in another reference frame. And we'll see a little more about what that means and implications for causality in a later lecture. But I want to wrap up with one of the most famous examples in all of relativity, and that's called the twin paradox. And I want to explain to you exactly how the twin paradox gets resolved. I typically get 2 or 3 emails a week from readers of my book on Einstein and from viewers of my other great courses that talk about relativity asking about this. So I'm going to be really patient with it, and I'm going to go through and show you exactly how this is not a problem. So here's the so-called twins paradox. We've already worked out this one-way space trip. In the Earth star frame, the time, delta t, was 12.5 years. In the ship frame, the time, delta t, prime, was 7.5 years. So here's what it looked like at the beginning of the trip. At the end of the trip, we were 12.5 years on the Earth and star clocks, which are synchronized. They're reading the same time at the same instant. The ship clock reads 7.5 years. Now let the ship turn around. The ship goes back. All the same mathematics applies. By the way, it applies because it's v squared in all those formulas, so the direction doesn't matter. The ship goes back. It takes another 7.5 years in the ship frame. Total time in the ship frame, 15 years. It takes another 12.5 years in the Earth star frame. Total elapsed time, 25 years. The ship is now had 15 years elapsed. The Earth star frame has had 25 years elapsed. If the ship's pilot was one twin and the other twin was left behind on Earth, they were the same age at the departure. The traveling twin, the one who went in the spaceship, is now 10 years younger. And you can do the math to leapfrog any amount of time into the future with this. Whoa, how is this possible? Well, there are several things that people seem to think are paradoxical about this, and I want to clarify 2 of them particularly. Shouldn't this effect be reciprocal? Why can't the twin in the spaceship say, oh, I saw Earth go off into the distance and turn around and come back? Well, to understand why that's not a problem is to understand what's special about special relativity. I mean, why doesn't the Earth star move away, turn around, come back? Or star time should be shorter, and clearly it isn't. The situation is not symmetric. It's not symmetric because the ship undergoes an acceleration and the Earth and star don't. And special relativity is only about unaccelerated motion. Special relativity only says the laws of physics are the same for uniformly moving reference frames. If you start to accelerate, you can't apply special relativity in your frame. You can apply it to the times you're not accelerating, which is what we did in that case, but we ignored that very short time when the ship turned around. When the ship turned around, this twin in the ship felt very great forces as the acceleration occurred, just like you feel when a jet airplane is taking off, only much worse. She felt pinned to the back of the pilot's seat and all this kind of stuff. Earth and star didn't feel anything when the ship turned around because it was only the ship that was not in a uniformly moving reference frame. So there is not a symmetry here. Now that alone doesn't explain why the 2 times come out different, but it gives you an out. It says, look, you can't make the argument that the ship observer should say Earth and star went out and came back and they should be younger because the ship observer is in 2 different inertial, uniformly moving reference frames during this trip. The Earth and the star stay in one frame. so the situation is not symmetric. Changes in motion matter in special relativity. Uniform motion doesn't matter. But now here's the deeper paradox. Shouldn't the observers on the ship conclude that Earth's star clocks run slow? In the way I did this problem, I suggested, well, here's the time in the Earth star frame, 12.5 years. They think that, quote, the ship clocks are running slow, and they get 7.5 years for the ship time. Now, you might say naively, I've said, okay, well, what does the ship observers think? Do they think, since the Earth star people think the ship clock is running slow, doesn't the ship clock think the Earth star clocks are running fast? Sounds reasonable, but if you say that, you're violating the principle of relativity. Because the principle of relativity says if you're moving uniformly, if I see something moving uniformly by me, I will apply that same time dilation argument because my frame of reference is just as good as anyone else's, and I will conclude that clocks moving past me are, quote, running slow. Again, remember, it's a little more subtle than that. It's about events that are occurring in frames of reference where they do occur at the same place or they don't occur at the same place. So, the answer to the question, shouldn't the ship observers conclude that the Earth star clocks run slow, shouldn't they conclude that? Yes, if they really believe in the principle of relativity, they should conclude that. Relativity requires that conclusion. So how can that possibly be right? How can the Earth star observers say, oh, the ship clock is running slow, but the ship observer says, oh, Earth star clock is running slow, and nevertheless, everybody agrees when the twin who was traveling gets out of the ship that she's younger than her brother who she left behind on Earth. How can that be? The answer is it's not a contradiction, and it's not a contradiction because events that are simultaneous in one reference frame need not be simultaneous in another. And let me end by drawing the picture again from the ship's perspective. And you'll notice in this picture, the ship is longer than it was because now we're in the ship's point of view. The Earth and the star are squished in the direction of their motion by that contraction. And the distance between the Earth and star is 6 light years. And there's no arrow on the ship because we're in the ship's reference frame. It's not moving. The Earth and star are moving to the left past it at point 8c. And here's the picture when the ship starts out. We've got 0 on the ship clock and 0 on the Earth clock. And I put some question marks in the star clock because I don't know what time the star clock reads. But I do know this. Events that are simultaneous in one frame of reference need not be simultaneous in another. So the events of the Earth clock reading 0 and the ship clock reading 0 need not be simultaneous. And in fact, they are not simultaneous. And in fact, without doing the math, and I could work it all out, but I'm going to just give you the number, and you'll see how this resolves the contradiction. What is in fact the case is that the star clock at this point is reading 8 years. That's the time on the star clock. The two clocks are not in synchronism in the ship's frame of reference. They are not synchronized. The star clock is 8 years ahead of the Earth clock. And again, I haven't proved to you mathematically why it's 8. We could do that with a generalization of time dilation called the Lorentz transformations, which give you the coordinates, x, y, z, and t coordinates of an event in one frame of reference relative to another. But this is what happens. And so now what's going on here? What is the thinking on all this? Well, at the end of the journey, the Earth and star have moved past the stationary ship, stationary in its own frame of reference. Now we know the ship clock reads 7.5 years. The question is, what do the Earth and star clocks read? Well, here's the ship's reasoning. The Earth and star clocks run slow. By that same factor, 1 minus v squared over c squared square rooted. That's the factor 0.6 that we calculated before. So they're going to have elapsed only 0.6 times 7.5 years, or 4.5 years. They're running slow, the ship says. But the star clock was 8 years ahead. So it now reads, it did read 8 years before, now it reads 8 and 4.5 is 12.5 years. The Earth clock read 0, so now it reads 4.5. And there is no contradiction. We've got the ship going by the star clock reads 12.5, the ship clock reads 7.5. From the ship's perspective, 7.5, 12.5, the ship says the star is going past me at 0.8c. In the Earth star system's perspective, the ship is going past at 0.8c, the ship's clock reads 7.5, the star clock reads 12.5, and all that matters is that we compare those two clocks at the same place, and there's no contradiction. The explanations are different. The ship says the star clock is running slow, but it's 8 years ahead of the Earth clock. The other perspective, the star says, this clock, the ship's clock, is running slow, but my clock is synchronized with the Earth's clock. They're both right, and they both give the same result, and they would give the same final result after the ship turns around again. Well, that is crazy, but that is what the principle of special relativity says. Let's wrap this all up. The principle of relativity implies that the speed of light has the same value for all observers in uniform motion because the principle says the laws of physics are the same for all observers in uniform motion. That leads directly to this formula for time dilation. Delta t prime is delta t times that square root factor. The time interval between two events is shortest in a reference frame where they occur at the same place. That leads also to length contraction. Length contraction says an object is longest in its own rest frame. That leads to the relativity of simultaneity. Events that are simultaneous in one reference frame need not be simultaneous in another, and that's the way out of most of the contradictions in relativity, including particularly the contradictions, or seeming contradictions, brought up by the twin paradox.